China assembled a cluster of over 10,000 domestic accelerators and reported training throughput that rivals what the United States built around Nvidia's best silicon. That did not take a decade. It took one product cycle. Nvidia's per-chip lead is real. By the numbers, it is still growing. The question that actually decides artificial intelligence supremacy is whether that per-chip lead can outrun the rate at which China is wiring thousands of weaker chips into a single machine. That is the race. That is what the next 15 minutes is about. A lead on the scoreboard is not the story. The story is which side's clock is moving faster on the dimension that decides the contest. Nvidia holds the chip clock. China is running a different clock entirely, the system scaling clock, and it is moving at a pace Nvidia's architecture was never designed to race against. To make this concrete, trace one thing all the way through, one training run, a single large language model training job from the moment it touches silicon. One rack, one chip, one interconnect, one cluster. To the moment the loss curve flattens and the model is done. That training run is the unit of competition. Everything that follows is about how fast each side can complete it and at what cost. Start at the chip level because the honest place to open this race is where Nvidia wins most clearly. Nvidia's H100 and H200 are the independently benchmarked standard for frontier artificial intelligence training. Their memory bandwidth, their floating point, throughput at reduced precision, and their high-speed chip-to-chip interconnect speed are public figures confirmed by labs and researchers outside Nvidia's orbit. The H200 extended the lead the H100 established. The Blackwell generation, now entering volume production by Nvidia's roadmap, pushes further still. The chip integrates high-bandwidth memory from fabrication partners at a density that China cannot yet replicate at the same node. Per chip, this is not a close contest. Huawei's Ascend 910B is the best publicly acknowledged domestic accelerator in China's supply chain. Huawei's own framing, and I want to be clear that this is a vendor claim, not an independent benchmark, places it in competitive range of an Nvidia chip that is one full generation behind the current H100 and two behind Blackwell. Reports from Chinese labs that have run workloads on both describe the gap as real, and in some memory-bound training jobs, wider than the spec sheet implies. The Ascend 910C is in development. No independent benchmark confirms its performance yet. Think of the chip as a runner's stride length. Nvidia's stride covers more ground per step. China's runner has a shorter stride. The training run on a single H100 completes more useful gradient updates per watt, finishes sooner, and produces a better trained model in less wall clock time than the same job on an Ascend 910B. That is Leg 1's entire verdict. Nvidia's clock on per-chip training throughput, the pace setter, confirmed by independent benchmark. China's clock on per-chip training throughput, roughly 1 to 2 Nvidia generations behind, by the vendor's own framing and corroborated analyst estimates. The gap on this leg, not compressing. If anything, the Blackwell introduction widened it. Now the same training run gets distributed across thousands of chips, and the race changes shape. My read going into this video was that China's cluster throughput numbers were largely a propaganda statistic, raw floating point operations assembled to generate a headline. After tracing the interconnect architecture described in supernode reports, I am less confident in that dismissal. The throughput claims are still unverified by independent benchmark, but the engineering path to get there is not obviously fraudulent, and that distinction matters. Nvidia's NVLink and NVSwitch interconnect architecture allows large numbers of accelerators to share memory and coordinate at high bandwidth within a node. Hyperscaler clusters in the United States run tens of thousands of H100s. The bandwidth and latency inside those clusters is a major part of what makes frontier training tractable at all. The networking hardware is not solely Nvidia's to control, but Nvidia sits at the chip center of the entire stack. China's answer to the per-chip deficit is system scale. Reports covering projects linked to state-backed compute initiatives describe supernodes wiring thousands of Ascend chips with domestically developed interconnect. A reported claim that one such cluster surpasses United States benchmarks by over 20% in aggregate throughput has not been independently verified. Treat that as a state-adjacent claim, not a confirmed figure. What is less disputed, China has stood up very large clusters of domestic chips faster than most Western analysts projected 2 years ago. The scaling pace is the signal. Any single throughput number is the noise, the stride rate answer to the stride length problem. If Nvidia's runner takes strides twice as long, China can match the split time by running a relay. Many shorter strided runners handing off faster than anyone expected the relay to be organized. The relay burns more energy. It requires far more coordination per meter. But the clock at the finish line does not care how elegant any individual stride was. The same training run, now sharded across thousands of chips. Each chip handles a slice of the job. The interconnect is the nervous system. China's chips are slower per slice. But if there are enough slices, the job finishes in comparable wall clock time. That is the entire logic of the supernode strategy. Nvidia's clock-on-cluster time to scale, a frontier-class cluster, tens of thousands of chips with full interconnect, has historically taken major hyperscalers 1 to 2 years from hardware commitment to training-ready deployment. China's clock-on-cluster time to scale. Reports suggest comparable scale achieved in roughly one product cycle, 12 to 18 months for state-backed compute projects. The gap on this leg, compressing. China is not ahead on quality. The rate of assembly is faster than the lead on this leg predicted, but running the cluster requires a continuous supply of chips, and that supply is where the third clock enters. Nvidia's supply chain runs through TSMC for fabrication and relies on extreme ultraviolet lithography equipment for leading-edge nodes. The United States export control regime has progressively restricted which Nvidia chips can ship to China. The A100, then the H100, then successively downgraded versions. Each tightening narrows China's access to frontier Nvidia silicon further. Nvidia has responded with compliant versions of its chips, but those versions trail the unrestricted hardware and performance. The control regime creates a ceiling on China's Nvidia access, and that ceiling is lowering. Huawei's Ascend line is fabricated domestically or via supply chains that do not depend on United States export-controlled equipment for the current generation. Though the leading-edge node question is genuinely unresolved, analysts flag real uncertainty about whether the most advanced Ascend chips use fully domestic silicon processing or partially processed silicon from SMIC. What is clearer? Ascend production volumes are increasing. Reports from the supply chain suggest SMIC is producing Ascend chips at scale on its most advanced available node, even if that node trails TSMC's cutting edge by at least one generation. Supply self-sufficiency is the fuel question. Nvidia's runner is faster, but the fuel, export-controlled chips, is being rationed at the border with each successive regulatory tightening. China is building a domestic refinery. The refinery's output is lower grade, but it cannot be cut off. The training run traced through leg 3. If export controls eventually sever all Nvidia access, China's training jobs run entirely on domestic chips. Leg 3 is about whether that domestic supply can keep the job running at all, not whether it runs well, just whether it runs. Nvidia's clock on China-accessible supply, constrained to downgraded versions, with the gap to unrestricted Nvidia hardware growing each product generation. China's clock on domestic accelerator supply, production volumes increasing quarter over quarter. Huawei and SMIC as the primary axis. The gap on this leg, compressing in volume, not in pure chip performance. China is supplying more chips, not better chips. 3 legs, 3 compressing gaps. Now, the honest break. The dimension that is not compressing is training efficiency. Useful compute per watt, per dollar, per unit of time, on the workloads that define frontier artificial intelligence. And this is where I think the standard read of the race is incomplete. China's cluster throughput numbers look fast because they are measuring the right thing on the surface, aggregate performance on a training job, but they are measuring it without showing the cost. Running more Ascend chips than H100s to complete the same training run means more power draw, more cooling infrastructure, more silicon area, and more interconnect complexity. The throughput can match on a headline scorecard, while the real resource consumption per unit of useful compute diverges, and diverges badly. Think of two cars completing the same lap in the same time. One does it at 30 miles per gallon, one does it at 8. The lap time is equal on the scoreboard. The fuel bill is not. In a race with 1,000 laps, that difference is the whole contest. An H100 cluster running a frontier training job at peak efficiency consumes enough power to light a small city block. A Chinese supernode reporting equivalent throughput, by the efficiency estimates implied in the gap between the chip architectures, would need to power a larger neighborhood to complete the same job. That is not a rhetorical point. It shows up in cooling systems, grid connections, and operating cost per trained model. The supernode claim, taken at face value, is a throughput claim. It is not an efficiency claim. Those are different clocks. The strongest case that Nvidia's efficiency lead is a mirage comes from software, not hardware. This is where the standard analyst call sits, and I think it is correct. But I also think the timeline on that moat is shorter than the consensus assumes. CUDA is Nvidia's deepest moat, not the chip. The 2 decades of optimized kernels, libraries, and trained engineers that sit on top of the chip. Chinese labs are not porting CUDA to Ascend. They are building from scratch on Ascend's CANN framework, which means every engineer trained on CANN is one fewer engineer dependent on Nvidia's stack. The moat is real. The permanence is the hypothesis I am testing, and I would not bet against that gap closing faster than the consensus timeline suggests. Because Chinese labs are not trying to replicate the past 2 decades, they are training the next generation of researchers to route around it from the start. Hold both cases at once. China can match Nvidia's training throughput on a per-cluster scorecard by spending more power and more silicon. It cannot yet match Nvidia's training throughput per watt, per dollar, or per unit of useful compute. That is the clock that decides which side can afford to keep running at frontier scale. The efficiency gap is real. It is not compressing on the current evidence. And it is the honest break on every compressing split from the 3 legs before it. The scaling pace is real. The efficiency gap is real. They are not the same race, and conflating them is how you misread which side is actually winning. 12 months out, Nvidia's per-chip lead holds and likely extends with Blackwell generation volume shipping at scale. China's cluster build-out continues, and at least one reported supernode deployment reaches a scale that makes the aggregate throughput comparison genuinely contested, not just on paper. Export controls tighten further, narrowing China's access to frontier Nvidia silicon for new purchases toward near zero. Domestic Ascend production increases but does not close the efficiency gap. The per-chip clock, Nvidia. The cluster scale clock, China gains. The efficiency clock, Nvidia, by a margin that is not yet under meaningful pressure. My call, stated plainly, China wins the cluster headline race within 12 months. A reported aggregate throughput number from a Chinese state-adjacent source will exceed any single Western cluster on raw floating point operations. That headline will be real, and it will be misleading at the same time. The training run I have been tracing through this entire video, the job that moves from one chip to one cluster to one finished model, will still complete faster, at lower cost, and with better output quality on Nvidia-centered infrastructure. Winning the clock on the scoreboard is not the same as winning the contest the scoreboard is supposed to measure. That training run, from silicon to finished model, is still ending faster on Nvidia's side. China is running more laps per day. Nvidia is running faster laps. Faster laps win for now. The question is how long for now lasts. And that answer depends almost entirely on whether software efficiency on domestic hardware can close faster than a new export control. Tightening resets the starting line. The chip that wins today is not the clock that decides tomorrow, but tomorrow is not a fixed date. And right now, Nvidia's tomorrow is still arriving first. Here is what I want you to leave in the comments. At what point does raw cluster throughput become good enough that efficiency stops mattering? And has China already crossed that line for some workloads without the industry noticing? Because if the answer is yes, the clock I said Nvidia is winning may already be the wrong clock to watch. If you want to keep tracking both clocks, not just the one the headlines pick, subscribe and turn on notifications. The next leg of this race is already running.